In this video, we're going to talk about application of the derivative. First, we'll go into optimization, and in a later video, linear approximation. All right, so let's recall relative extrema. If you recall, when we talked about behavior of functions in curve sketching, relative extrema, we have the relative maximum or the relative minimum. In an open interval, f of c is the relative maximum if f of c is greater than all other function values within the open interval. That's why it resembles a hill. It's the highest or the largest value among a certain open interval. F of c, on the other hand, will be called relative minimum if it's the lowest among a certain open interval. So there. The relative extrema is usually the peaks and the valleys of a certain graph. And it's what we call this. It's not the highest and the lowest value of the graph because our graph can extend from negative infinity to positive infinity. So we are only concerned with the peaks or the hills or the lows or the valleys. If you would recall, we have actually two tests that we usually have for us to determine whether a certain critical number rather, is a relative extrema. If you would recall, usually for us to get our relative extrema, we first get the first derivative and either equate it to 0, given the function y is equal to f of x. So we get critical numbers at f of x equal to 0 or at f of x is undefined or does not exist. So the numbers here, x will be what we call our critical numbers. There. From the critical numbers, we then decide whether, depending on if you use the first derivative or the second derivative. If you would recall, the first derivative test, would tell us that if the f of c from decreasing to increasing, that means f prime of x before f of c, f prime of x is less than 0, then after f of c, f prime of x becomes greater than 0, then it is a relative minimum. In the second derivative test, f double prime of x should be less than 0 for it to be, not less than 0, but greater than 0. So it should be greater than 0. So for the first derivative test, if either it's decreasing before the critical number and increasing after the critical number, or at the second derivative is greater than 0, it's a relative minimum. For a relative maximum, then at fc it should be increasing first, so that's f prime of x is greater than 0, then decreasing, f prime of x is less than 0, or at the second derivative it should be less than 0. So we can use these two different tests for us to determine relative extrema. Now, one of the most common applications of calculus that would involve extrema would be the determination of minimum and maximum values for optimization. Optimization is that process wherein we want to find the greatest profit or the least cost, the greatest or the least area. Because we want to optimize, we want to use the limited resources we have to the most optimal or to the best that we can use them. So may we, of course, for example, in businesses, we would like greatest profit with the least cost. There are certain situations wherein we have to use the least area possible to save some materials, or we would have to cover the largest maximum area possible. depending on the situation. So now we're going to use the concept of relative extrema to find these maximum and minimum values. So here are some guidance for us to solve problems involving optimization. First, we identify all given quantities and quantities to be determined, just like how we usually solve a problem. We give all the given. If it's possible for you to make a sketch, do so. Now, next one would be we have to write an equation for the quantity to be optimized. So there should be an equation wherein we're going to find the relative extrema, either maximum or minimum, for that equation. Now, reduce the equation form into having one single independent variable. Remember, we just have one dependent and one independent variable. So, if you would have more than two independent variables, for example, in the formulas for area, for volume, if there will be such cases, we have to reduce the equation's form into having one single independent variable. This may lead to us to analyze if there are other relationships involved in the problem. And then we have to make sure that we have the feasible domain, the only possible values of x, because remember, for example, we don't have negative time. We don't have negative measurement. So we have to make sure that we are working in our feasible domain. And then after that, we now determine our maximum or minimum values using either the first or second derivative test, whichever you think is more applicable. So let's have some examples. First one. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum one? So, for number one, we want to design an open box. Let's have an open box. Circular box. This one here. So we are assuming that this one here is open. The rest are my box doesn't like this. My arrow rather doesn't like it's pointing at the top. Alright, so momentarily I thought I was looking at a different way. So we have the 6 spaces here, and this let's shade instead our closed spaces. Oops, it's not there. So this is a closed part of the box. This is also a closed part of the box below. Here we go. This is another one. This is closed part of the box. And this one also. So the one on top, the one with a color yellow, is the one I'm going to highlight the border of that with blue instead. This one here is open. That's why I did not shade it red, because what we're seeing now is like the inside of the box. So this one there is open. So it's here on our image. So the base of the box is supposed to be a square. So the one on top and the one below, this is a square. Having a surface area of 108 square inches. What dimensions, length, width, and height will produce the maximum volume? So, first, from the surface area of an open box will only need the area of the base volume and the area of the 1, 2, 3, 4 parallelograms that will serve as the lateral faces. So with this, our surface area would then be equal to the area of this. The area of the box of the square here, area of the square plus 4 times the area of the lateral faces. 1, 2, 3, 4. If we're going to let the side of the square base be x, because that's what we have, we're working with the surface area, we have the surface area is equal to x squared, that's the area of a square, plus 4 times each lateral face here has this side as one side, and then this side here, the height of the box, as another side. So since the area of any parallelogram is base times height, x as the base of the parallelogram, h as the height, so we're going to have 4 times x times h. Since we want the surface area to be 108, therefore the equation we have formed so far, that x squared plus 4xh is equal to 108. That's what we have. But we want to maximize volume, and the volume of any solid is usually the area of the base times height. So the volume would be the area of the base, which is x squared, times height. If we want to maximize volume, then this is what we would have to maximize. However, if you recall, we need to make sure that the equation that we need to find the derivative only has one independent variable. Hence, we need to somehow remove that h and make it x, so that it's easier to find the derivative in terms of x. And we can work it out most probably using this equation, because it's the x squared plus 4xh equals 108 is that equation that contains both x and h. In doing so, we're going to solve for h. Let's transpose x squared, so that 4xh is equal to 108 minus x squared. Divide both sides by 4x, then the height is equal to 108 minus x squared over 4x. With this in mind, substituting it here, then we go to have the volume is equal to x squared times 108 minus x squared over 4x. This then simplifies to v is equal now to x times 108 minus x squared over 4, which then turns out to 100. The volume is equal to 108x minus x cubed over 4, which is easier for us to find the first derivative, for us to find the critical number, for us to find the extrema. So now that we have the equation that we can find the derivative, let's now find the derivative of this in terms of x, and then find the critical number. So, derivative of v in terms of x will be equal to, we can actually separate this, since this is 4, we can for easier finding of the derivative, we would like to separate this in terms of like v is equal to 108x over 4 minus x cubed over 4, which then turns into 27x minus x cubed over 4. So, if we're going to find the derivative of v in terms of x, it will become 27 minus 3x squared over 4. There you go. Now, since we want to find the maximum volume, we need to find the critical number to find the relative extrema. And that means this 27 minus 3x squared over 4 should be equated to 0. Because remember, to find extrema, we need to find the critical number. The critical numbers are the numbers that make the first derivative 0 or not exist. And there won't be any numbers that would make this not existing because the function becomes quadratic. All we need to do is solve for x squared. So we transpose this, we have negative 3 fourths x squared is equal to negative 27. Divide both sides by negative 3 fourths. This gets cancelled, and we're going to have x squared is equal to 36. We get the square root x to the equal to positive negative, 6. That's positive and negative 6. Now, we first have to double check. Since this is a measurement, we cannot have a negative value. So therefore, we can only have x is equal to 6. So the measure of x should be equal to 6. So therefore, since they're both the same, the next thing that we need to find the dimensions of the height only because the length and width of the box is actually the same. We were able to get h here. So therefore, to solve for h, that would be 108 minus x squared over 4x. And that will then be 108 if x is equal to 6, so 6 squared over 4 and 6. This is then would be equal to 3 inches. Now, the question is, are the dimensions that we found 6 by 6 by 3 the relative maximum? Is the dimension will give us the maximum volume. The question now is if 6 is 6 gives us a relative maximum. So you may do different tests. Since the derivative is a polynomial, I can use the second derivative test for me to easily determine if 6 is a relative maximum or relative minimum. So, to find the second derivative of b in terms of x, that will then be equal to, this becomes 0, and then I'm going to have, it's negative 3 times 2x over 4. So we're going to have negative 6x over 4, which is equal to negative 3 times x. So the second derivative of the function is negative 3 times x. And if I put x is equal to 6, then the second derivative would automatically be negative. Let's put there. It's negative 9. Since the second derivative is negative at the critical number, then this is a relative maximum. Second derivative is negative, therefore it is a relative maximum, which is what we need. So, having x as one of the dimensions, because it's a square, so that's one of the dimensions, will give us the maximum volume. Therefore, what are the dimensions of the box? We have 6 inches by 6 inches by 3 inches. And that's one example of an optimization problem. There you go. Let's have another example. Let's just clean out the area. So, the graph of y is equal to negative 1 half x plus 2 encloses a region within the x and y axis in the first quadrant. A rectangle is at the enclosed region has a vertex at the origin, and a vertex of the graph of y is equal to negative 1 of x plus 2. We're asked to find the dimensions of the rectangle so that the area is a maximum. So, we are to do number 2 here. We are told that we have the graph. Okay. So, this is so most probably it's this line here. It's probably that. Maybe we can make it big. Alright, there you go. I have now somewhat larger coordinate axis. So this is 2, so so the line that we horizontal of this. Although we can extend the distance to this. There you go. So this is the line y is equal to negative 1 of x plus 2. So we have an enclosed region here in the first quadrant. And there is a rectangle whose vertex is here and whose vertex is probably somewhere here. So for example, I make this rectangle this way. Oops. There you go. So we have this rectangle here. One vertex at the origin and another vertex at this line. Now, with that in mind, we now have to find the dimensions of this rectangle so that it has a maximum area. So it's kind of difficult and not that difficult, but it's kind of more abstract compared to the first problem. How do we first do this? Now, we have this equation, meaning all the y values of this line is equal to this. Given any x, we can find the value of y there. Which would mean that this point here would have an x coordinate and a y coordinate of negative 1/2 x plus 2. What would that mean now? That would mean that if this is the coordinates of that specific point, that means its abscissa has a length of x and its ordinate would have a length of negative 1/2 x plus 2 because that's the value of y. And we know that the area of a rectangle is equal to length times width. In this case, it's x times y, which in this case would be x times negative 1/2 x plus 2. That's the area of the triangle because we have the width as x and the length as this. Again, the reason why this is negative 1/2 x plus 2 because that's actually the height from this to this point, which is that negative 1/2 x plus 2 are the y values or the coordinates of all the points on the given line. Now that we have a here, a will then be equal to negative 1/2 x squared plus 2x. This is now what we find our critical number. So finding our critical number here, dA, let's solve here down below. So, given that the area is given by the equation negative 1/2 x squared plus 2a, the first derivative of that equation in terms of x would be equal to negative, if we bring down this one here, that's negative 1/2 times 2x plus 2, going to have actually negative x plus 2. So, since this is our first derivative, we would have to equate this to 0 or make it undefined to find the critical number. Since the value is the function that the first derivative became is a linear one, it does not have a value that would make it not divisible. Instead, we have to equate it to 0. So, therefore, this will then become negative x plus 2 equals 0. And easily enough, x is equal to 2. So the question now is 2, will 2 give us a relative maximum or a relative minimum? What we need is a relative maximum based on the problem. So, easily from the first derivative, we can actually get that the second derivative of this is automatically negative 1. And since the second derivative is negative, at the critical number, it's already a maximum value. So we're good. This is already a maximum value. All we need now to do is find the dimensions of the rectangle. So if x is equal to 2, this is actually 2, although my drawing seems to be inaccurate now because it has to be here. Here, I use a different thing. So it's up to this point. The x value, the y value now will then become, oops, the y value, which is negative 1 half x plus 2, would then become negative 1 half times 2 plus 2. This gets cancelled. We're going to get negative 1 plus 2, which is equal to 1. So actually, the rectangle that can give us the greatest area has an x at negative 2 and at y at 1, which is here. So actually, the rectangle with the largest area looks like this. There you go. Just like this. The rectangle in red. That is the rectangle that with the highest, with the greatest area. Now let's go to number 3. As you can see, different problems will have different ways of analyzing. So we have to be very careful in analyzing this because there's no one step-by-step guidelines, but we have to look at it carefully individually. So next, we are asked to find the dimensions of a right circular cylinder of greatest volume that can be inscribed in a right circular cone with radius of 5 centimeters and height of 12 centimeters. So we're asked to find the dimensions of a right circular cylinder. This is our cylinder. And then we are asked to find the dimensions of this of greatest volume that can be inscribed inside the right circular cone. So we're looking for a cylinder. A cylinder that is inside a right circular cone. That's why I was to actually draw with the cone first. So for example, we have this cone here. There we go. We want to add, so inside this cone is actually a cylinder. So if this cylinder already has the greatest or the largest volume, what would be the dimensions of this cylinder? Given that the radius of the right circular cone is 5 centimeters and the height of it is 12 centimeters. So since it's the cylinder that we would like to find the greatest volume, we start with the fact that the volume of a cylinder is equal to pi r squared h. And we either have to use r or h as our independent variable. Now, the relationship that we can have so that we can replace r or h is from the volume of the cone. The volume of the cone is actually equal to 1/3 pi r squared h. Which gives us the same dilemma that we have two independent variables in our figure. How do we go about this? Now, in geometry, we have this specific shall we say, concept that, here you go. As you can see here, I'm going to highlight that in the purple. This is the height of the cone, then this is the radius of the cone. We form a triangle here. With the radius of the upper base of the circle, we form this figure that looks like the figure forms something like this. So this is the first triangle form, and then here on top which serves as the the radius rather, of the upper base of the cylinder, we form this triangle. These triangles rather. So the height is 12. That's 12. This is 5. This is 5. And then we have this h here as the height of our cylinder. And this is the radius of our cylinder. In geometry, we have this relationship that these sides are proportional. If I'm not mistaken, this is called the mid-segment theorem, that the ratio of the mid-segment of a triangle would be equal also to the mid-segment to the part of the larger triangle is equal to the ratio of the corresponding part of the smaller triangle with the mid-segment to its corresponding part on the larger triangle. What would I mean is that if I'm going to get these ratios, the ratio of the radius which serve as the mid-segment of the triangle to the radius of the cylinder which serves as the base of the bigger triangle, that's r over 5. That's the same as the ratio between this line segment and then the entire 12. The line segment here on top is the result when you remove h from 12. So that's 12 minus h. So from here you can solve values whichever you would like to solve. We're going to do cross multiplication here. We're going to have 12r is equal to 60 minus 5h. So whichever is easier for us, that's what we do. It looks like it's easier if we divide by 5. So we can do this. So I'm going to have 5h is equal to 60 minus 12r. With that in mind, it's easier to divide both sides by 5 because if you have a larger denominator, say 12, it might be a bit more difficult to work with. So instead, we have this one and h is equal to 60 minus 12r over 5. So with that in mind, we can now change, we can use this now to place it in the volume of the cylinder. That's what we have to find the derivative. So with that in mind, the volume of the cylinder now becomes pi r squared times 60 minus 12r over 5. Which gives us now the derivative of, the equation of 60 pi r squared minus 12 pi r cubed over 5. Since we want to find the first derivative, let's simplify this fraction here. So I'm going to have the volume is equal to, this becomes 12 pi r squared minus, this one here sticks to 12 pi over 5 r cubed. So that if we find now the first derivative of the volume in terms of r, this then becomes 24 pi minus, this is a constant now, so we can simply have, we can simply now have 12 pi over 5 times 2 r squared. And it really becomes 24 pi minus 36 pi r squared over 5. With that, we now have to be able to solve. We now have to be able now to solve or find the first derivative of this. Sorry, the first derivative. I'm talking about the critical number. The critical number now, since it's again a polynomial function, we just need it will not have any value that will make it not existing. Hence, we first need to solve 24 pi minus 36 pi over 5 r squared equals 0. So, we actually have a common factor here. So, This is R squared, so there should still be R. So since we have a common factor here, actually take the common factor of 12 pi r. 24 and 36 are multiples of 12. So taking out pi and r as well, we'll have 12 pi r times 2. What is that? R already, so that's it. Yeah, so that's 2 minus 3r over 5. So there you go. Factoring out 12 pi r. From 24 pi r minus 36 pi over 5r. So with this in mind, we can now equate this to 0. So that would be 12 pi r. By zero product property, this separates, so 12 pi r equals 0 and 2 minus 3r over 5 equals 0. So this side dividing both sides by 12 is still not work. R is equal to 0. Here, we just need to transpose this. I'm going to have negative 3/5 r is equal to negative 2. We divide the both sides by negative 3/5. We have here r is equal to 10/3. That is 10/3. So of course we don't want a radius of 0, so we get to this. Now let's first check if this is a relative extremum. More specifically, we need the greatest volume, so it's a relative maximum. Now based from our derivative, which is this one here, maybe it's easier if we look for the second derivative of this one here. So this derivative here. So for the second derivative, squared b over b r squared, we're going to find the first derivative of the first derivative. That will give us 24 pi minus 72 pi r over 5. Finding the second derivative of the original function, which is the first derivative of the first. So if we're going now to replace here 10/3, that would be 24 pi minus 72 pi times 10 over 3. Alright, so, oops, it's not supposed to be 10, but 10/3. So if we substitute 10/3 here, our second derivative is actually negative 56 pi. Since this is negative, therefore the second derivative is less than 0, which is again a relative maximum. Since we have already proven that what we have is a relative maximum, then the radius is 10/3 centimeters. For the height, the other dimension of the cylinder inside the cone, we just need to solve for height. So height will then be equal to 60 minus, we will now have 60 minus 12 times 10/3 all over 5. So this will then become 60 minus 4 over 5, which is then equal to 20 over 5 is equal to 4. So therefore, the dimensions of the cylinder should have a radius of 10/3 centimeters and a height of 4 centimeters, so that it has the greatest volume right inside the cone. So those are examples of problems in optimization.